Hello, welcome. This is a Digging Deeper video. We're going to talk about true conditional false hypothesis. This is discrete mathematics in the summer of quarter 2024, and I'm the instructor, Charles Wichorek. Conditional statement. What do we mean by a conditional statement? In the English language, it has a form, something like this. If hypothesis P, then consequent Q. Now, you won't see it written like that anywhere, but the idea is if something, then something else. In formal notation, and this, of course, is in the context of our formal notation study in discrete mathematics, in formal notation, we use an arrow. We write it as P arrow Q. And the arrow is important. It's directional. I'll talk more about that later. I'm going to read this as P then Q. So the idea is that if we know that P is true, and we assert that P then Q is true, so that statement, P then Q, we're saying that's true, and P is true, then what can we do? We can assert that Q is true. If the hypothesis is true, then we can assert that the consequent is true. We use this all the time. If it's Thursday, I'm going to teach at 1 o'clock. Given that we have the true values in the right places, it should be the case. One thing you should notice here, I defined this, I said the idea is that if we know that P is true and we assert that P then Q is true, then we can assert that Q is true. But I used if and then in here, so this language of conditional form, this is very fundamental to thinking and to thought. Just like all the piece parts, the fundamental piece parts of logic are really embedded in our thinking process. And so is this if-then. So it's almost impossible to define it without using it. So the arrow operator is defined with the following truth table. So a truth table, we put down the variable names P and Q in the left two columns. And then we say, what's the value, true false value assigned to P then Q with those combinations of P and Q. And here's the truth table. If P and Q are both true, we assign a true to P then Q. If P is true and Q is false, we assign a false to P then Q. And I'll talk more about this later. If P is false and Q is true, we assign a true. If P is false and Q is false, we assign a true. This is the standard table for the conditional operator in formal logic. And just to repeat, when we assign this, we assign true to all the rows except one. We assign a false only to the row where P is true and Q is false. And that should make sense. We want to assert that, if P then Q and P true, then Q must be true. So if P is true and Q is false, then the if P then Q must be false. But that table, this one here, with those true, false, true, true assignments, it's often troubling to students. The students will agree with the assignment of true and false to the first two rows. True, P true, Q true. Okay, P implies Q should be assigned true. The second row, P true, Q false, as I just mentioned, we want to assign false to P then Q. And that's all comfortable. But students puzzle about the last two assignments, the assignments in the last two rows. P false, Q true, we're going to say P then Q is true. P false, Q false, we're also going to say P then Q is true. I guess the puzzling comes from the false P and the true for the then. In this video, I'm going to try to explain why the truth table must be coded in this way. We'll look more closely at the characteristics of the conditional form in the English language. How does it work in the English language? What are its restrictions? We'll then examine all the possible ways to assign truth values to P then Q. when P is false. In other words, what are all the possible ways to fill in these two rows in the table with truth-false values for P then Q? So let's do a review of the conditional statement. Once again, a conditional statement is in propositional logic. It encodes the English language sentence form if hypothesis P, then consequent Q. And we're going to interpret the conditional statement, this entire if statement, and its constituent clauses, the hypothesis P and the consequent Q. We're going to interpret those as logical statements. And what do I mean by that? A logical statement is a deductive sentence that can be judged as true or false, and not both true and false. We have to be able to say it's explicitly, without doubt, true, or it's explicitly, without doubt, false, and there's no going back and forth. The common encoding of this conditional statement you've already seen, P arrow Q. This symbol, this arrow symbol, it should help remind us that this is a directional operator. The direction of the arrow is important. It's P, then Q. That order is important. But what is the essence of this statement form? Here it is. When the conditional statement P then Q and the hypothesis P are both true, the consequent Q must also be true. That's it. That's the very essence of it. If you're asserting that this if-then form is true, and you assert that the P in the form is true, then it must be the case that the Q is true. That's what we mean. That's the essence of the if-then statement. So let's go through and build our truth table line by line so that we can finally come to some agreement as to why it's built in the way it is. So we're going to start, and we're going to use the essence of this statement to fill in the first two rows. From the essential meaning, I think you can all agree that when if P then Q, the operator, the conditional operator, P then Q, if that's true and P is true, then by the essential meaning of the statement, the consequent Q is true. So true, true, true. And from that same meaning, we want to say that P then Q must be false if you have the combination P true and Q false. If it wasn't false, if it was true, then we really wouldn't have anything in the essence of this statement. P being true would imply Q true or false, and we wouldn't know anything about Q. So we want to rule this one out, and I think everybody can agree to that. But we need to define all four rows. We need to assign true-false values to P then Q for all the assignments to P and Q. So we have two left over, P false, Q true, P false, Q false. And this is where the subtleties arise, as I've already mentioned that. Should P then Q be considered true or false in the last two rows of the truth table? There's always a question about that. But before I look at all the possibilities, before we look at all of them, let's agree on rules for interpreting a conditional statement in the language. So I think that there are two rules. The first is the essence. If we assert both statement P, then Q, and statement P, statement Q is also asserted. That should make sense. This is, as I say, this is sort of the essence of it. You want to have this agreement that if this P arrow Q is true and P is true, you want the arrow to indicate that Q must be true. The second rule is somewhat the same. If we assert both statement P then Q and the statement Q, so now not the statement P but the statement Q. So the rule says that if we do that, if we assert the statement P then Q and the statement Q, not the statement P, the statement Q, then the statement P is not to be asserted without more evidence. So this is important. In fact, it's at least as important as the first rule. P then Q is directional, and so is Q then P. If we turn it around, there should be the possibility for a difference in interpretation. The assertions of the two directions should be independently true or false. They should not dictate to each other. Let's look at some examples. Here I have P then Q. If it snows tonight, I will stay home. P is the proposition, it snows tonight. Q is the proposition, I will stay home. And then we have the form if with an implied then. If it snows tonight, then I will stay home. Let's assert that P then Q is true and P is true. If we do that, I will stay home, Q, must be true for logical consistency. By the definition of the essence. Remember, the essence of the form tells us that if we assert P then Q and assert P, then we must assert Q, which would tell us I will stay home. Let's turn this around and now let's consider Q then P. If I stay home tonight, it snows tonight. I turned it around. Remember, Q is I will stay home. I put that in the hypothesis. P was the old hypothesis. I moved that to the consequent. Given that P then Q is true and Q is true, we cannot conclude that Q then P is true. Okay, let me read that one more time. Given that P implies Q is true, occasionally I'll slip and say implies. We got to be careful with that word. There's a bit of a dissension in the definitions of logic to using implies for this symbol, just because it has more implication has more power than we want to give to this statement. So anyway, I'm going to try and remember to say P then Q. Given that P then Q is true and Q is true, we do not want to conclude that Q implies P is true. This was that second principle. We want the independence of the two. Okay? We want to say that it does not conclusively follow that if I stay home tonight, then it snows tonight. And obviously I may have another reason to stay home. So this is an example that should make you believe that there's an independence here. I can assert that if it snows tonight, I will stay home. But if I assert that I will stay home, along with if it snows tonight, I will stay home, I cannot assert the converse. I cannot assert that I will stay home, then it snows tonight. We want that independence. We can break the independence by making one change. Let's write, I will stay home tonight only if it snows. So this is a way in the English language to break the independence. What is the hypothesis? What is the consequent? So we still have, if it snows, I will stay home. They're just kind of reversed. If it snows, I will stay home tonight. But the if now has this only in front of it. Only if it snows. What does that mean? The only if it snows is interpreted in this way. If it does not snow, I will not stay home. Does that sound right? Only if it snows. If it does not snow, I'm not going to do it, right? I'm not going to stay home. Let's put this in formal notation. Not P, it does not snow, then not Q. I will not stay home. But let's look at the contrapositive of this statement. And the contrapositive is equivalent, has the same truth values as this statement. The contrapositive would be reverse and negate. Not Q, then not P. But we can use turn double negation. It's equivalent to just not negating at all. So we would say this contrapositive for this case is equivalent to Q implies P. Not Q is equivalent to Q, not P is equivalent to P. This statement, the contrapositive, is equivalent to Q, then P. And let's put it into the English language. If I stay home tonight, it snows. So by saying, I will stay home tonight only if it snows, I can assert that if I stay home tonight, it snows. Let's assert both of these, both directions. Let's assert P then Q and Q then P. If it snows tonight, I will stay home. That's P then Q. And, there's the and, the conjunction. I will stay home tonight only if it snows. Remember, that's the Q implies P. So this can be written formally as P then Q and Q then P, but more succinctly and more commonly, it's written with a double arrow. P double arrow Q. It indicates both directions are in play here. P arrow pointing to Q, Q arrow pointing to P. We read this as P if and only if Q, and you can see how that follows from what I showed in the example. So we can assert P if and only if Q together with either P or Q, and we'll achieve a result in both cases. Right? If we assert this dual arrow conjunction conditional, P if and only if Q, if we assert that, and then we assert P, we can assert Q. If we assert this double arrow conditional and we assert Q, then we can assert P. It has both of the directions inside. Why am I going through all these? Because I want to convince you that the truth table for the conditional statement must support all these common examples. The way that we assign the true-false values to those last two rows must be compatible with these kinds of interpretations. So let's go back to deciding on the truth values for the last two rows of the table. We have four possibilities. We can assign false and false to P then Q. And notice the last two rows are when P is false. So we could assign false and false, or another case we could assign true and false, true to the case of false P, Q, true, false to the case of false P, false Q. Or we could assign false and true, false to the case false P, true Q, true to the case false P and false Q. And one more case. We could assign true and true. And of course, we've already seen that this is what we'll want to end up doing, but we need to justify this. True and true. True when we have false P and true Q, and true when we have false P and false Q. Let's examine these possibilities one by one, left to right. So the one on the left, the first one on the left, we're going to choose P then Q false whenever hypothesis P is false. We have a false and a false. There's a problem. We've just duplicated the truth table for the AND operator. True, false, false, false. The AND operator is only true if all of its operators are true, not operators. Operands are true. We don't want P then Q to be the AND operator. The AND operator is not directional. If this was true, then P then Q and Q then P would both always be true together. That would be the time that whenever we assert this, we'd have to have both of them true. And that's AND. That's not what we have for our two laws, our two rules. And we're going to say this rule violates the second. This case violates the second rule. It doesn't allow for the independence of these two directions. So let's look at the second case. We're going to choose P then Q true for the case P false, Q true, and we're going to choose P then Q false for the case P false, Q false. Okay, it's just the second instance. But take a look at the columns. If I read down the P then Q column, I have true, false, true, false. If I read down the Q column, I have true, false, true, false. In other words, I now have a table where P then Q is equivalent to Q because the respective columns are equal. So when P then Q is asserted, Q must be true regardless of the value of P. So when I assert P then Q, I've got to have Q true whether P is true or not, true or false. So I'm going to rule this out and say this violates the spirit of Rule 1, where we want to have some significance to P being true in this conditional, some significance to Q. And we would not have no significance in this case. Let's look at the third table from the left. Here we'll choose P then Q false for the case P false, Q true, and true for the case P false, Q false. You can read that right up here on the table. But this choice, it shows us that a true conditional, here we go, true conditional on the first row, true conditional on the last row, that would allow us to assert that the truth values of the hypothesis and the consequent, P and Q, must be the same. We have TT for PQ on the first row, FF for PQ on the last row. This is somewhat like an exclusive or, kind of the opposite, but nonetheless, you can see there's a binding here that we don't want. They would make P and Q equivalent when asserting P then Q. And again, I'd say that this violates Rule 2. It kind of stands in place of their independence. So we're left with the last possibility, assigning true to both cases, true whenever the hypothesis P is false. Well, Rule 1 is clearly supported. That's the same in all these tables. Rule 2 is supported, and that's what we need. We need to support Rule 2. We need to support this in several ways. If P then Q is true and P is false, we want Q to have either truth value. And we'll see that that occurs in this table. P then Q is true. We see that in the first row, the third row, and the fourth row. But P is false. We see that in the third and fourth row. We want to say we know nothing about Q in that case. And that is given in this table because Q can be true or Q can be false. So that's good. When we have a false instance of P, we can't say anything about Q. And so, we don't have any extra knowledge beyond what we allowed in the essence of the conditional. We support the essence in another way. P then Q is true, and Q is true. So let's look where that is. P then Q is true. So there are three places for that. And Q is true. Well, Q is going to be true in the first row and the third row. Here it is. The first row, Q is true. The third row. We can see there that in that first row, Q is true and P is true. In that third row, Q is true and P is false. So here we have this somewhat sort of a reverse case of what we just looked at. Here, if we know that Q is true, if we assert P then Q, and we know Q is true, we can't say anything about P. We don't know. It could be true or false. And that supports the directionality. In both the cases that I've shown here, we maintain the directional nature of the operator, which we must do. All right, I hope this convinces you that the only assignment of truth values to P then Q that agrees with the conventional English language meaning of if P then Q is the assignment of all rows except for the row with P true and Q false, all rows true. Right? Assignment of true, let me read that carefully, is the assignment of true to all rows except for the row with P true and Q false. There we go. We have the three trues and the one false, just as we started with. Thank you.